Okay, so today we're going to start talking about telescopes. This is the last chapter in the radiation unit. Um, so we have optical telescopes, and this is how a refracting lens works. To refract something basically means to bend it. So a refracting lens bends the light as it's coming through. And what you hope with a lens is that you bend it down to one focus, one focal point. And the distance from the middle of that lens over to the focal point is what we call the focal length. Another type of optical telescope is a reflecting telescope. So, where rather than using lenses, you use mirrors. So, there, the focal length is the farthest point on the mirror to the focal point there. And basically, you use a bent mirror so that you bend it all back to one point. So these are just two simple examples of reflecting versus refracting telescopes. So this is the refracting telescope where you have a lens here and then an eyepiece lens here as well. And the focal length would be the distance from the objective lens out here to the middle there at the focus. The reflecting telescope comes down here. Here's the primary mirror. Then that focuses the image on the secondary mirror or just past it, and then that reflects it out to the side to the eyepiece, so you can see it over there. So modern telescopes, our best ones anyway, are all reflectors. So the light traveling through lenses reflect, and this is why I should say, light traveling through lens is refracted differently depending on wavelength. Some light traveling through the lens can be absorbed. Large lenses can be very heavy and can only be supported at the edge, otherwise you block some of the light that's coming through. The lens needs two optically acceptable surfaces, whereas a mirror only needs one. So if you think about a mirror, it just bounces off one surface, whereas a lens, the light has to go through one side, go through the lens itself, and then go out the other side. So it has to be much more perfect. So and this is basically just showing the first part of that, where different wavelengths of light will actually get refracted differently, which will lead to a fuzziness in the image, because like the red part of the light here would get refracted less than the blue part. So things just wouldn't be in focus nicely. So here are some different types of reflecting telescopes. You don't need to memorize all these, but just notice all the different examples here. So you have the prime, which is very basic, and then Newtonian is the one they gave you in the other slide, where it shoots it out the side over here. Cassegrain bounces it back through kind of through the middle of the mirror, and then Naismith bounces it up here and then back and then out the side. So all different ways to do this. The Keck telescope. This is one of our best observatories, one of our best ground-based telescopes that we have. It's in Hawaii at Mauna Loa. And that has a whole bunch of hexagonal mirrors. That's what this picture down here is showing. So all these hexagonal mirrors bounce the light up to here, then back to a reflector. The Hubble Space Telescope has a variety of detectors. It has a whole bunch of different things that it does. But the primary mirror is inside here, and then you have this hatch that lets the light in. Hubble Space Telescope's main mirror is 2.4 meters in diameter, about 10 feet, and is designed for visible, infrared, and UV radiation. So we have telescopes that use all the different parts of the spectrum, not just the visible. So here we compare the best ground-based telescope image of M100, which is a galaxy, on the left with the Hubble image on the right. And you can just see much, much clearer, more defined with the larger mirror and being out in space. So with telescopes, the light gathering power improves detail. So size does matter with telescopes. So the brightness is proportional to the square of the radius of the mirror. So this B was taken with a telescope twice the size of A. You can see it's much bigger, brighter, much more detail involved. So resolution is the ability of the telescope to distinguish two separate points of light. So you can see here, this would be like improving resolution with better telescopes of the same thing. So here it looks kind of like one big fuzzy patch. Improve the resolution a little bit more, and it looks like, okay, well, you can kind of start to see that you have two fuzzy patches, but they still look connected. And if you have a really good telescope, then you could actually tell that those 2 points of light are actually separate and distinct. So once again, bigger is better with telescopes. So here are just pictures showing the effect of improving resolution, the brightness, the crispness of the images. Points of light look distinct rather than one big blur. We're not going to necessarily talk about diffraction and stuff like that, so we'll skip over that. Basically, this is saying that we can now use computers to sharpen up images, which is nice. The technology works for us. Atmospheric blurring occurs because the air in the atmosphere is moving around. So the light gets scattered a little bit. So what do? We put the telescopes on mountaintops, especially in deserts, because in the deserts, you're going to have less water vapor, less stuff to get in the way. And if you put them on mountaintops, that just makes the atmosphere and the air thinner. But obviously the best place to put them, but they're more expensive and harder to deal with, is space. If you put them in space, then you don't have to have the problem of looking through the atmosphere. And you can kind of see in the background of this picture, like how many particles there are in the atmosphere that you're actually looking through if you try to look down from the bottom. Active optics can control the mirrors based on temperature and orientation. So what they do is they shoot a laser up through the atmosphere and measure it, and then adjust the mirrors based on what that laser measures as it's going through. So these are just some examples of different ways that we use this. We also have radio telescopes, less sensitive to imperfections due to longer wavelengths. They're very, very basic, and they just look at the radio waves rather than the visible light spectrum. Here's what was formerly the largest. China now have made one bigger than this, but this is Arecibo in Puerto Rico. So this is 300 meters, so like 3 football fields across. It's like they scooped out the top of a mountain and then filled it with concrete. So signals come down from here, bounce up to the detector, and then they listen to it and get the images processed through a computer. But it gives us totally different information. So this down here is showing, this is a visible light image with a radio image over the top of it. So these lines here are what you would get from the radio portion of this. And this is basically telling you that, hey, this is the center of this is where you're getting the most radio waves. The good thing about radio telescopes is it doesn't have to be dark. So you can do radio astronomy 24 hours a day. Doesn't matter if there are clouds, rain, snow, none of that gets in the way. And you get different information because you're looking at a different part of the spectrum. And if you don't have one huge disk, you can string together a whole bunch of dishes. And the resolution in this case will be dependent on how far the farthest dishes are away. So the farther away you get the dishes working together, then the better the resolution will become. And that's called interferometry. So you can get radio image whose resolution is close to optical if you use interferometry, and you can see the image on the left versus the image on the right. The right is visible, the left is a radio telescope. Infrared radiation can image where visible radiation is blocked. Generally can use optical telescopes, mirrors, and lenses. And these are just, so visible on the left, infrared on the right, and notice it cuts through all the clouds and the haze. So this is the same image with both. And same thing up here. You get to cut right through all the clouds in this nebula and see what's going on inside. So it's pretty cool. Here is infrared of the Orion Nebula. So here's the Orion constellation. Here's the Orion Nebula right down there. You can see the sources of heat using the the infrared telescopes as well. Spitzer Space Telescope has an infrared telescope in it, and we put it in orbit around the sun to get some very cool images that way. We also take UV images, but we have to get those out of our atmosphere because our atmosphere blocks the UV rays. And then there are also X-ray and gamma ray telescopes that are very difficult because of the high energy nature of the particles. So here is an X-ray image of a supernova remnant. And here is a gamma ray image. Can't really be focused at all. You can just kind of see where the gamma rays are coming from. And here are all the different parts of the spectrum using telescopes for each different thing. So this is the Milky Way. Right here, it's right across the middle, using visible, radio, infrared, X-ray, gamma ray, everything. So we need all the information in order to get the best picture.